This conference will now be recorded.
Hello everyone. Under chemical properties of aldehyde and ketones, we are discussing oxidation reaction. Now under oxidation reaction, we have some reaction that are considered as identification test for aldehyde. That is, if you want to differentiate between aldehyde and ketone compounds, you can do this test. So all the four tests we have discussed. The last test was shift test, and based on that, we have here one question. Okay, and in today's class, after finishing oxidation, there will be reactions related to reduction reactions and related problems, and if time permits, then the next type of reaction, which is reaction involving alpha hydrogen. So here the question we have, why does glucose doesn't undergo shift test? So one question in last class we have discussed, where we have seen that if you consider glucose for tolerance reaction, okay, then this reaction is positive, but in this case, that is for shift reagent, or you can say shift test, glucose does not undergo this test, that is negative test is there. Now glucose, it can remain in open chain form and in cyclic form, in both form. Now when it is in open chain form, as you can see, this is the Fischer projection formula. This is a CHO group, and as CH2 group is present, it should give all the reactions that are possible for aldehyde, that is CHO group, right? And that is why tolerance reaction, it is positive. But remember, in case of shift test, as we are discussing oxidizing reactions, that means here CHO group, it is acting as reducing agent, and the reagents that we are using in oxidation reaction, that reagents are actually oxidizing agent. Now we have to also keep it in mind that whether these oxidizing agents that we are using in this identification test, whether they are strong or weak, because if they are not strong enough, then this type of ring open and ring, whether it will remain in open form or not, that is also, it may differ. So another point is, here we use basic condition. Right now, in basic condition, this type of ring opening and ring closing, all this can happen. So whether this basic condition it is weak or not, that we have to consider. So though it is true that glucose contains aldehyde group when it is in open form, as you can see in the first picture, but it forms a cyclic acetal structure which is known as pyranose. So this is known as D-glucopyranose. So this type of there is equilibrium. As you can see, there is equilibrium sign. So when it is in straight chain form, that is Fischer projection formula that we are seeing, the first picture, there is equivalent sign. That means you can write the same molecule in this form. Numbers are given, you can easily check the numbers. So this is the CHO group here, and the last CH2OH. Now why we have written this molecule in this way? Because only if you write it in this way, you will be able to understand that this oxygen, which is OH group, which is present at 5 carbon, that is actually attacking the C double bond O. So now if you rotate the bond, which is coming towards CO, so now the attack, we can easily show this type of mechanism, right? As a result, C double bond O is broken, and there is formation of hemiacetal type of cyclic acetal type of structure, right? Now why it is so? It is actually hemiacetal, because hemiacetal means carbon, there are any groups present, one OH and one OR. So here you can see there is one OH, there is one OR. OR is basically this side, if you consider, this is a large OR, and one H and another group. So as there is one OH and one OR, so that is why it is hemiacetal, and as it remains in this that is ring structure, so it will be not able to show the test for aldehyde. So this structure, that is the cyclic structure, it is very stable and is not broken down by the shift reagent, which is weak base. In tolerance test also there is basic condition, but basic condition whether it is weak or not, that we have to keep it in mind, right? If it is weak, then mostly it will remain in the cyclic form, it will not remain in the open chain form, And if it is not remaining in the open chain form, obviously the test for CHO group is not possible. So that is why when we are treating it with Schiff reagent, it will give negative Schiff test. Fine. So that is important observation, which is not in case of other test, that is Tollens test. So after finishing the oxidation reaction, now there is reduction reaction. Now first process for reduction is, that is reduction reaction means aldehyde ketones in presence of some reducing agent, they will be reduced to some other compounds. Now the first type is reduction to alcohol. That means you will take aldehyde molecule, ketone molecule, you will treat all these molecules with some reducing agent, and you will get the end product is alcohol. Now for details, this is already discussed in the chapter alcohols, phenols, ethers, in under the topic preparation of alcohols, because in this reaction the product is alcohol. So that is why it is under preparation of alcohol, how you can prepare alcohol. So how we can prepare alcohol, one of the method is by reducing aldehyde or ketones using some suitable reducing agent. So all the details are there. Okay, next type of reaction is if you are using some reducing agent which is reducing aldehyde or ketone to hydrocarbon, not alcohol. In alcohol it is converted to COH, but now it is CH2, not alcohol, there is no oxygen. Now for this, what reducing agent we are using, the carbonyl group of aldehyde ketones, they can be reduced to methylene group. Methylene group means CH2. Don't be confused between methylene and methyl. Methyl is CH3, methylene is CH2. Fine. So methylene group is generated from CO. There may be any other groups both side depending on whether you have taken aldehyde or ketone, but ultimately you are getting, in place of C double bond O, you are getting CH2. And what reducing agent we are using here, it is simply mentioned 4H. That means hydrogen molecule we have to use. Now under this reduction to hydrocarbon, some that is A, B, C, some more that is different types we will see. So under 2, that is reduction to hydrocarbon, under this heading we will have the first reduction, which is Clemenson reduction. Now why we have this variety? Because in all cases it is ultimately the end product is hydrocarbon. Then why we are discussing A, B, C under different heading? It is because of the different reducing agent we are using. End product is same, it is always conversion of C double bond O to CH2, but reducing agents are not same, conditions are not same. Fine. So here we have taken PHCOR. These are maybe any alkyl group or hydrogen, that is aldehyde or ketone, and we are using the reducing agent which is zinc amalgam. It is written in this way, Zn-Ag marker. So it is zinc amalgam, acidic condition. Remember, this condition is very important to remember, because sometimes it may happen, though here we have taken very simple molecule PHCOR, but that may not be the case always. Suppose you have taken a molecule where there is some acid sensitive group, so obviously your purpose is only to convert CO to CH2. Rest of the part you don't want to disturb. But if it is a rest of the part there is some acid sensitive group, aqueous HCl condition, that is acidic condition, we cannot use, because in that case the other parts of the molecule will not remain intact. So that is why you have to keep it this fact in mind, that whether the substrate that you have taken for reduction purpose, whether there is any acid sensitive group present or not. In that case you cannot use this method. So here CO group is converted to CH2. Some examples. Here the first molecule is there is some benzene ring, but now we have taken acetaldehyde in presence of zinc Hg and hydrogen concentrated HCl, we are getting ethane. Now this CO is converted to CH2 and already one H is there, so ultimately it will be converted to CH3. Then CH3 CO CH3, that means acetone. Ketone we have taken, so this part will be converted to CH2, and that you can see here, and both sides there is CH3 CH3. So ultimately we are getting hydrocarbon. That is why it is reduction to hydrocarbon. Fine. This is Clemenson reduction. Next type is B, Wolff-Kishner reduction. Now this is a name reaction. Aldehyde and ketones when heated with hydrazine. Here reducing agent is hydrazine and sodium ethoxide, that is NaOET, OCH2CH3, sodium ethoxide. Now this is the basic catalyst and we get hydrocarbon. So what we do for, remember here the condition is basic. In the previous reaction we have seen condition is acidic. Okay. Aldehyde ketones first converted to its hydrazone. We know when there is C double bond O present and you are treating with some ammonia derivative. Remember the first type of reaction where we have the nucleophilic addition. Under that heading we have discussed one reaction which is ammonia and its derivatives. They are acting as nucleophiles. So this is same thing. So here ammonia derivative is NH2NH2 which is N2H4, that is hydrazine, and 1H2 and this CO if you remove there will be condensation reaction. That means C double bond NH2 will be produced first, which is the hydrazone intermediate. Now when you are hitting it with strong base, ultimately you are getting ethane. So two examples we have taken, one is acetaldehyde, another one is acetone. Some more examples we will see. Acetophenone, PHCOCH3 in presence of NH2NH2. Now here only one step is shown, but now the reaction that you are seeing in the box, here you can see the intermediate also. So first this NH2NH2 which is acting as nucleophile, the lone pair over nitrogen, it will attack this carbonyl carbon. There will be COH generation and ultimately after water removal we will get CN double bond. So this is hydrazone of acetophenone, but finally this C double bond end will be broken and in that place we will get two hydrogen, and this is occurring in presence of NaOET, basic catalyst, right? So two nitrogen atoms will be removed in the form of N2 molecule, that is nitrogen molecule, and heat is also there. Ultimately we are getting ethyl benzene, CH2 CH3 group attached to benzene ring. Cyclopentanone, cyclic ketone we have taken, so same intermediate again. Here it is shown cyclopentanone hydrazone, but finally this C double bond N, in this position there will be 2CH2. So the net conversion is conversion of C double bond O to CH2 group. Then cyclohexanone, same type of reaction, cyclohexanone hydrazone produced first, and finally we are getting cyclohexane molecule. So these are the examples of Wolff-Kishner reduction. Remember, Wolff-Kishner, we mentioned both are actually conversion of CO to CH2, but condition is different. In the first case, the condition is drastic. We are using some concentrated acidic condition, but here it is basic catalyst, that is basic condition. So if you have some groups which are sensitive to base, then obviously this method is not applicable. So all these things we have to keep it mind. Fine. The third reaction type under reduction, that is reduction to hydrocarbon, is Raney-nickel desulfurization. What is Raney-nickel? Raney-nickel is basically nickel, but this is a special kind of nickel which its appearance is grey powder-like form. It is actually the alloy with aluminium. It is nickel aluminium alloy, but mostly here the nickel is the actual catalyst. So what it can do, this reagent, its special property is to reduce carbon sulfur bond to carbon hydrogen. But if you are thinking where from carbon sulfur is coming, because we are discussing aldehyde ketones, there is no question of carbon sulfur bond, right? Then why the question arises CS bond is converted to CH? Actually here the starting material for Raney-nickel desulfurization, that is that will be formed from the aldehyde or ketone. So first you have to make the substrate from aldehyde and ketones, and then you have to use Raney-nickel. So this is the two steps. So that is why at a first glance it seems that it is not under aldehyde or ketone, but actually it is so. Now when combined with formation of thioketal, remember we have discussed acetal. Now in place of acetal, we take 2 alcohol, but instead of taking 2 alcohol molecules or 2 OH group in the same molecule, if we take 2 SH group, which is analog of OH, in that case, the acetal that is formed, we call it thioketal. So first we have to generate this thioketal from a ketone, and this is also an alternative means for converting ketones to alkenes. Here we have started with RCOR, ketone. First you have to convert it to this type of thioketal, and for that purpose we are using this molecule HSCH2CH2SH, which you can also write in this form, CH2CH2SHSH. So this is just analog of, remember, this type of molecule. Just in place of O, you have sulfur. Sulfur, oxygen, they are from same group, group 16. So they will behave, there will be some similarity. So SH group and this O, if you consider the removal of this H and O, there is formation of 2 carbon sulfur bond. So these are the 2 new carbon sulfur bond. You are getting thioketal. Now this is the substrate when you can use ranitidine nickel in presence of hydrogen, obviously, because ultimately this carbon sulfur bond will be broken, and in that place you will get 2 new CH bond, right? So ranitidine nickel, it is actually converting CS bond to CH bond, that is mentioned in the first point. Fine. Another example, here we have taken cyclic ketone in presence of same molecule. Again we have taken thioketal is generated, and writing it here. In presence of ranitidine nickel ETOH, actually here hydrogen should be mentioned. There is reduction of this CS bond to CH. So directly you cannot apply it to ketone or aldehyde, but first you have to convert to thioketal, then only you can use it. Now one important thing, the first reaction under reduction to hydrocarbon prevention, where the condition is acidic. Next reaction, Wolff-Kishner, condition is basic, and now the reaction that you are seeing, it is neutral. So 3 different conditions, but all are same type of conversion. So after finishing reduction to hydrocarbon, the next type. So under 3 we have seen ABC. Now we have reached 3. Sorry, under 2 we have seen ABC, 3 types. Now 3, reduction to phenol. So the first reaction, number 1, reduction to alcohol. Details you can find in the chapter alcohol phenol ethers under the topic preparation of alcohols. Next reduction, reduction to hydrocarbon. Third reaction, reduction to phenol. Now what is phenol? This is a molecule which is basically symmetrically substituted 1,2-diol. 1,2-diol means 1,2 position, there will be 2 H group, and both sides there will be same type of group, that is what is symmetric. So this reaction involves reductive homocoupling of a carbonyl compound. So you will take 2 carbonyl compound, there will be radical generation on carbon atom, and that 2 carbon radical will be joined together and it will form a new CC bond, where this 1,2-diol, that is the final molecule 1,2-diol. So here the first step, single electron transfer of the carbonyl bond. So 2 molecules of acetone we have taken. Here the reagent, there is magnesium metal. So what it is doing, suppose this C double bond O, you are writing it in this way, that is break the pi bond, put negative charge and positive charge. Now under this condition, if the metal is giving 1 electron, then 1 electron will be received by C plus. So now it is anion radical. I am talking about this moiety. These 2 are anion radical because it is anion O minus as well as it is radical also. So I am calling it anion radical or radical anion. Now these 2 C dot, they will join to each other. Single headed arrows are used because it is single electron. You will get a new CC bond in this position. Fine. And these 2 O minus charge, that will coordinate with this Mg2 plus. Now how it is Mg2 plus? Because it has already donated 2 electron to 2 acetone molecule. So now it has lost 2 electron, oxidation state 2 plus. So OMG bond. But finally water in acidic condition will be used, and OMG will be, that is in this position there will be 2 hydrogen. So the first step, single electron transfer of the carbonyl bond, which generates radical ion intermediates, and that will undergo coupling, CC coupling. Ultimately you will get 1,2 diol. So this is 1 position, this is 2 position. Now both sides you can say this is symmetrical. There may be any other groups. In this case it is methyl, but there may be other groups, though here yield is not very good. So this type of basic 1,2 diol, that is actually known as pinnacle, and different groups may be present both sides, but that is same. Fine. So this is also reduction reaction, because ultimately it is accepting electron from magnesium, right? C double bond O, now it is converted to COH. So based on this reduction, let's see this problem. Here one conversion is mentioned, RCOR is converted to RCH2R. That means it is reduction to hydrocarbon. Remember, we have just discussed. So you have to identify number of reagent that can be used for this conversion. Here how many reagents are given? A, B, C, D, E, F. Total 6 reagents are given. Out of these 6, how many can be used for this type of reduction? That we have to see. The first reagent that is given, ZnHgHCl. Remember, this is Cleveland reduction, where we use zinc, amalgam, and concentrated HCl condition. So obviously this can do, that is, it will be able to do this conversion. Next reagent is lithium aluminium hydride. Now lithium aluminium hydride, if you use on RCOR, then RCOR will be converted to secondary alcohol. Now if you are thinking why I have not discussed it, because that is discussed under the topic reduction to alcohol. Details you will find in the other chapter. So now it is alcohol. So it is not converting CO group to CH2, it is converting CO to COH. So this cannot be correct. Next, CaCl to NaOH. Now this reagent combination we use in Reimer-Tiemann reaction, where some CHO group is inserted in the benzene ring. So this is completely different types of reaction. No question that it is correct. Then option D, actually it is not option, you have to just count the reagents. Hydrazine in alkaline condition. Remember, hydrazine in alkaline condition, in which case we have used? We have used it in Wolff-Kishner. Though their HO minus is not shown, NaO it is shown, but any basic condition we can do this reaction. Okay, so this reagent Wolff-Kishner, that is also, and that can also be used. Then number E is Raney nickel, right? So first you convert this RCOR in presence of CH2SH, it will be forming this type of thioketal, and then on this thioketal, if you treat it with Raney nickel and hydrogen, it will be converted to RCH2R. So this can also do this reaction. And SiO2. Now this is oxidizing it. This is not at all reducing agent. So this is cannot be used, right? So out of 6, total 3 reagents we can use. A, D, E. Here in this question we have the reagent NaBH4MeOH. Now this is also a reducing agent which is used for conversion of keto group to alcohol. And this is not very strong reducing agent, unlike lithium aluminium hydride, which is very strong. Now lithium aluminium hydride, it can convert not just ketone carbonyl, aldehyde carbonyl, it can also reduce ester carbonyl. But NaBH4 is not so strong reagent, it is comparatively weak, and that is why it is more selective. In this molecule we have CO group, we have ester, and we have CC double bond. Now all these 3 groups are prone to reduction. When keto is converted to, that is reduced, it will be converted to OH. When ester is, suppose I am writing it, rest of the part I am not writing, COCH3. If this is reduced, it will be converted to CH2OH. And if CC double bond is reduced, it will be converted to, that is, 2 hydrogen atoms will be added. Now we are using NaBH4MuH. This can reduce, it cannot reduce ester, because ester carbonyl group, if you consider its the carbon's electropositive character is very less. Why it is less? It is because of this type of resonance. If you draw the resonance structure, it is like this. Now because of this type of resonance, the double bond character of carbon is reduced, because now you have single bond between carbon and oxygen. So the electropositive character of carbon is reduced. So as a result, the attack by nucleophile to this carbon, actually here when you are using NaBH4, it is the source of hydride ion, and this hydride ion is actually the nucleophile which will attack here. But this type of attack for ester carbonyl, it is not very preferred process, because now the electropositive carbon is electropositive character of the carbon is reduced. So that is why ester group carbonyl, it is not very prone to that is by nucleophilic attack, because the positive character of carbon is very less. So that is why NaBH4, as it is not very strong like LiAlH4, which is very strong. So this is not so strong. So this can reduce C double bond O of this carbonyl, which is normal carbonyl, ketone carbonyl, but not the carbonyl group of ester. So rest of the groups, there will be no change. Option 4 is correct. See here, CC group is intact, ester group is intact. Only this part you have some change. So that is why it is correct. If it is lithium aluminium hydride, then this will not be, obviously not be the correct option, right? So option 4 is the correct option. Reaction involving alpha hydrogen. Now after this finishing reduction reaction, next type of reaction is involving alpha hydrogen. Now when I am saying alpha hydrogen, first you have to understand what is alpha hydrogen. The carbon attached to carbonyl carbon, that is alpha carbon. So if you consider this carbonyl carbon, that is this carbonyl compound, then this is CO group. The next carbon is alpha carbon, and the hydrogens that are attached to this alpha carbon, they are alpha hydrogen, right? So these alpha hydrogens, when they are taking part in reaction, that reactions we are now going to discuss. That is why the name reactions involving alpha hydrogen. And under this we have the first reaction, aldol reaction. Now this reaction is very versatile. Questions related to these reactions, it is very, very frequent. So you have to understand it very carefully. Aldol reaction. So it is obviously involving alpha hydrogen. So first, the carbonyl compound, it must have alpha hydrogen. Otherwise, why we are discussing this under this topic? It must have alpha hydrogen. If you consider some carbonyl compound, there is no alpha hydrogen. For example, if you take PHCOH, there is no alpha hydrogen, right? So it is not for that. You have to take, that is for generation of the carbonyl, you have to take the carbonyl compound which is having some alpha carbon, because when there is alpha carbon containing, actually we need alpha hydrogen, not alpha carbon with alpha hydrogen, and those hydrogens are, that is these two hydrogens, they are very acidic in nature, and the reason is because carbonyl group is present adjacent to it, so it is electron withdrawing group. So these hydrogens are acidic, and when you are using basic condition NaOH or KOH, the hydroxyl ion HO minus, that can capture these hydrogens, there will be generation of negative charge. So in presence of dilute base NaOH or KOH, two molecules of an aldehyde or ketone having alpha hydrogen, they will be add together. Ultimately, final compound is beta hydroxy carbonyl compound. So look at the second picture. This is alpha position, this is beta position, right? Now this is R group, this is R prime. Basically two molecules will be required. So RCOCH, now first there will be carbanion generation in this position, and that carbanion will attack carbonyl carbon of second molecule. And here you are getting now COH at beta position. So that is why the name beta hydroxyl carbonyl. because beta position there is hydroxy group. And finally, if you heat it, if you do not heat it, it will not happen. If you heat it, then what will happen? The hydrogen here and the OH both will be removed in the form of water, and you are getting CC double bond. So this is alpha beta unsaturated system. So the second step you can call it condensation. That is the dehydration step. This is condensation, okay, or dehydration, because water molecule is removed. In first, there will be formation of beta hydroxyl carbonyl compound, which is readily losing one water molecule. Ultimately, you are getting alpha beta unsaturated compound, because alpha and beta position there is unsaturation. That is why the name is so. This is known as aldol condensation product. So the first compound, you can say this is simply aldol addition product. Why addition? Because one molecule is generating carbonyl and that is added to another carbonyl group. That is why it is addition product. And the addition product, when you are heating it, there is removal of water molecule and you are getting some alpha beta unsaturated compound, right? Now if we look at the mechanism, the first step is deprotonation of the alpha carbon in presence of base. So in presence of HO minus base, here we have taken CH3, CH2, this molecule we have taken CHO, propanaldehyde. So this is the carbon which is alpha carbon, these two hydrogens alpha hydrogens. So this hydrogen is removed, there is generation of carbonyl. Now this carbonyl, it can undergo resonance and there is another structure possible. These two are resonance structure. Suppose this is 1, this is 1 prime. Resonance sign is there. So these two are the resonance structures. Because of this type of resonance, this carbonyl, or you can say enolate, this is enolate. Try to understand difference between enol and enolate. Enol is CC double bond COH. But when you are removing the hydrogen, there is negative charge over oxygen. That is why the name enolate. So carbonyl after resonance, enolate. So this carbonyl in the next step, now there will be addition reaction. This carbonyl is acting as nucleophile. It is attacking the carbonyl carbon. And you can see from the color, though both are same molecule, both are propanaldehyde, but one is in blue color, the first molecule where the carbonyl is generated, and that is added to the second molecule which is red color. So the red color compound, it is that is acting as the this carbonyl group, it is attacked by this carbonyl of the first generated carbonyl. So after that, there is a new CC bond formation in black color. Fine. So next, from water it will take proton and you are getting beta hydroxyl carbonyl compound. And the next step, if you heat it, there will be removal of water. And ultimately what you will get? Ultimately we will get double bond. Fine. So this acidity of alpha hydrogen atoms of carbonyl compounds, it is because of this strong electron withdrawing effect of carbonyl group, and resonance stabilization is possible for the conjugate base. So what is conjugate base? Conjugate base means suppose you have any acid HA, and when you are removing the proton, what you get by applying some base? What you get? You get A minus. So A minus is basically the conjugate base. So when you are removing this proton in presence of base, you are getting conjugate base. So this is conjugate base, these two, right? And because of this type of resonance, this conjugate base is very stable. So as it is very stable, so that is why it can attack the next molecule, which is same molecule, right? So this is the aldol reaction. Fine. Now what about ketones? Because in the previous examples we have seen aldehyde, though this particular structure, it is not aldehyde, or whether it is aldehyde or that is not clear because R groups we have not mentioned. You can consider it as if it is a general example, that is it may be aldehyde or it may be ketone. But remember, for aldehydes these reactions are better when it is ketone compared to aldehyde, because of obviously the electronic factor, steric factor. The reactions are not so good as you have seen in aldehyde. Aldol reaction can also occur with ketones as well. However, unlike the aldehydes, now the equilibrium does not favor the aldol products. If you look at the equilibrium sign, this is aldehyde molecule, this is ketone. Now in case of aldehyde, the forward sign that is longer in red color. You are getting the product. So this is one part. This is the same molecule, propanaldehyde, that we have seen. Sorry, it is butyraldehyde, not propanaldehyde. 4 carbon. 1, 2, 3, 4. So 2 molecules you have taken. One part you are getting from one molecule, another portion you are getting from another molecule. But important point is that the forward sign is longer. That means it will mostly remain in the product side. But for the ketone, second example, under same condition, now the backward arrow is longer in red color. That means it will mostly remain in the reactant side, not product side. So here you can understand, first there will be carbonyl generation and that will attack another cyclopentanone and ultimately you will get this structure. Though here the condensation step is not shown, but if you heat it, water molecule will be removed and you will get alpha beta unsaturated compound. And mostly the water molecule will be removed in such a way so that there is double bond generation in alpha beta position, right? So why I am saying so? Because if you remove this hydrogen and OH, you will get structure like this. Now alpha beta unsaturated carbonyl compounds are very stable because this CC double bond can take part in resonance with the C double bond. But if you are removing, suppose you are removing this hydrogen or this hydrogen, now what type of product you will get? You will get product like this. But this is not alpha beta unsaturated carbonyl compound. Okay, see, this is alpha position, this is beta position, this is delta position. So it is beta delta, it is not alpha beta unsaturated. So that is why these hydrogens will not be removed, only these hydrogen. But important point that we are focusing here is that when you compare ketone and aldehydes, aldehydes are preferred. Now there are some special distillation technique. By applying, we can increase the yield of aldol product for a ketone. Now the reverse reaction for converting aldol product of a ketone to the starting material ketone, that is actually very fast, because see here the backward arrow is longer. That means if you have some aldol product as a starting material which you have obtained from ketone and now you are doing the retro reaction, it will be called retroaldol, and that reaction is very faster for ketone because here the backward arrow is longer. It will mostly remain in the ketone form. So see, the same product in the second example we have taken, and this is example of retroaldol. So as if this H is removed, there is negative sign generation, and this is forming a double bond. This CC bond is broken. Ultimately you are getting a free cyclopentanone, another cyclopentanone which is carrying some negative charge. But this molecule, as you can follow this arrow, in presence of water it will be converted to cyclopentanone. So ultimately you will get 2 molecules of cyclopentanone, right? And this cyclopentanone in presence of HO minus, it can again generate this carbon. So there is 2 arrows, HO minus and H2O. It can convert to each other, right? But this is retroaldol. Another example, which is very common example, that until this you have seen we have used NaOH or KOH, but you can use BaOH2, which is just analog of NaOH, though it is not so strong. But barium hydroxide, Na and Ka, sodium, potassium, they are from group 1. Barium is from group 2. Its metallic activity, if you consider, comparatively low. Its basic character is low, but we are using it here for acetone or propanone. Two molecules we have taken in presence of this BaOH2. First, there is carbonyl generation will take place in any of this methyl group, and that carbonyl will attack another acetone. So as if this part you are getting from one acetone molecule and the other part you are getting from another acetone. And the name is 4-hydroxy 4-methyl pentane 2-O. Because if I do the numbering, this is the longest chain, 5 carbon. At 4 position you have hydroxy, you have methyl. H comes before M, so 4-hydroxy, then 4-methyl pentane 2-O, 2 position CO group. Now when we are heating it, there will be removal of water. So this OH and this H, not the other H at 5 position, because if you remove that, double bond will be generated in this position, which is not alpha beta unsaturated compound. So it will be removed in such a way you are getting alpha beta unsaturated compound. So this is CO, this is alpha position, this is beta position, it is alpha beta unsaturated product. Name is 4-methyl pent 3-in-2-O. Again, this is 2, 1, 2, 3. 3 position double bond. 4 position you have methyl group, and this is 5. Longest carbon chain, 5 carbon. So that is why the name 4-methyl pent 3-in-2-O. Aldol condensation product. The first product is addition product, that is nucleophile generated from the base. You are getting the addition product, and then finally after water removal you are getting condensation product. Now we will see some examples. It is not based on aldehyde or ketone, that is involving different types of molecules. So more examples you will see your practice, then it will help you to understand that how versatile this reaction can be, right? Now this example that you are seeing here, two different molecules we have taken, right? One is acetone, another one is benzaldehyde. Now in benzaldehyde there is no alpha hydrogen, but here you have alpha hydrogen in acetone. So that is why carbonyl will be generated in acetone, and that carbonyl will attack here in this carbonyl carbon. And also see the CHO group, carbonyl group, and this carbonyl group you consider, obviously this is more active. We know aldehydes are more reactive than ketones. So in presence of 10% NaOH, it will mostly remain in the condensation product. See, this part is generated from acetone and the other part is generated from benzaldehyde. Now, as there is one more CH3 group, so it is possible if you treat this molecule with again a 10% NaOH and another benzaldehyde, there is again carbonyl generation possible, so it can attack from the right hand side also to another benzaldehyde. So ultimately what you are getting this type of product. So 2 times aldol reaction is occurring, both sides of the acetone molecule. Next reaction, we have taken again benzaldehyde. So here we do not have any alpha hydrogen, so no question of carbonyl generation. Carbonyl will be generated from the other carbonyl. Now the previous example, the carbonyl compound is symmetrical, but in this case it is not symmetrical. You have 2 alpha position. So see, this is 1 alpha position, this is alpha prime position, so that you can differentiate. Now the interesting thing is, when you are treating this molecule in acidic condition, you are getting one type of product. Now this is also alpha beta unsaturated carbonyl, alpha beta unsaturated carbonyl. But if you are treating with 10% NaOH, again you are getting alpha beta unsaturated, right? But aldol reaction you have seen only in basic condition, but sometime in acidic condition the same type of product generation is possible. But how it is possible, that we will see, and why we are getting different product, that is also important question. So when it is acidic condition, what happens first? The carbonyl carbon that will be protonated because it is now in acidic condition. So let me write it. So this is the actual molecule. Now when it is present, that is in presence of H plus, what happens? Enolization first will take place. Now when we are talking about enolization, the enol will form in such a way that the CC double bond that you are getting, that will be very stable. So if this CH bond is broken and you are getting the enol, it is like this. Okay, so this is enol formation in acidic condition. If you are thinking why not the other position, if you consider the other position, the enol will be something like this. But here the CC double bond and the CC double bond that you are getting in the first case, obviously the first one is more stable, so that is why this will not be formed. This CC bond is more substituted, so this enol is more stable. Okay, so in acidic condition, first this type of enol will form, and now once it is formed, this PHCHO molecule, if we consider, that is benzaldehyde, this OH bond broken, now there is attack from this position. So basically the new CC bond that is formed, it is like this. OH, H, PH, and finally you will remove the sorry, there is C double bond. Finally there will be removal of H and OH. So this H and OH will be removed and you are getting CH3CO, then CC double bond. See, you are getting basically this product, right? But when it is NaOH, that is basic condition, now what happens? Now you have to consider which alpha hydrogen is more acidic. Because it is basic condition, it will deprotonate, it will form some carbon. Now these alpha prime hydrogens, if you consider, these hydrogens are more acidic compared to normal alpha hydrogen. That is alpha prime hydrogen more acidic than alpha hydrogen. Why? Because here you have one more methyl group which has some plus I effect. So because of this plus I effect, the acidic character of these two alpha hydrogen, that will be somewhat reduced. But that is not the problem if you consider these three alpha prime hydrogen. There is no such plus I effect. So that is why these are more acidic in nature, and the carbanion will generate in the left hand side. Now if carbanion is generated in the left hand side, attack will occur from this position. So see, this is the methyl group, this part is basically coming from CH3CO, CH2, CH3. So this CH2, CH3, now it is written as C2H5, and the other part is coming from benzyl. So this is very interesting example where using different conditions we can get different alpha beta unsaturated. Fine. Next reaction, here we have taken CH3, CH2, CHO, propanaldehyde, and two molecules of formaldehyde. Right? Now why it is so? Again, this formaldehyde, there is no alpha hydrogen because you do not have any alpha carbon. So no question of alpha hydrogen. Carbanion will generate only in the other molecule. Now two alpha hydrogens are there. So first alpha hydrogen, when you are removing, this will attack one CH2H. So this is coming from one CH2H. Then another hydrogen is present. If you also deprotonate that, you can attack another formaldehyde. So that is why you are getting this type of product. So if you are getting this type of question, be very careful why two CH2H two formaldehyde molecules are given for only one molecule of propanaldehyde. It is because of this type of reaction. Okay. Now we have taken this aldehyde, which is furan aldehyde. Furan molecule is this heterocycle, and you have CHO group. Now here also we do not have any alpha hydrogen because this is the alpha position, right? There is no hydrogen. So carbanion will generate in this molecule 2-methyl cyclohexanone. Now see both side, that is 2 alpha carbons are there. 2 different types of alpha hydrogens are there. Left hand side alpha hydrogen, right hand side alpha prime hydrogen. Now which alpha hydrogen is more acidic? Obviously alpha prime hydrogens are more acidic because here you do not have any class I effect problem of methyl group. So that is why carbanion will generate at this position and it will attack this carbonyl carbon that is present in furan aldehyde, and ultimately you are getting this type of molecule that is after it is a condensation product. It is not the addition product. Addition product is beta hydroxycarbonyl and condensation product is alpha beta unsaturated form. So this part we are getting from 2-methyl cyclohexanone and the other part we are getting from furan aldehyde. Now the next reaction that we are going to discuss, you already have some idea about the next reaction. So I'm talking about cross aldol reaction. So when it is cross aldol, you take 2 different aldehyde molecules or 2 different carbonyl compounds, right? In the previous slide you have seen we are using same molecules 2 times. But in all these examples, see carefully, we have taken 2 different molecules. And in all these examples, one carbonyl compound there is alpha hydrogen present, another carbonyl compound there is no alpha hydrogen. So if you can take this type of combination, one factor which is convenient for us is that you will get less mixture of products. Because suppose if you have taken 2 carbonyl compound A and B, and in both A and B there is alpha hydrogen. So now the problem is sometimes it may happen A will generate the carbocation, it will attack B, or it may be the opposite one, B can form carbanion, it will attack A. So this is cross aldol. But think about the other possibility. B can attack another molecule of B, that is carbanion of B attacking another B, carbanion of A attacking another. So 4 different combinations we will get. But if you restrict the condition that only one molecule there is alpha hydrogen present, other not, then you are bound to generate carbanion only in that molecule which is having alpha hydrogen, not the other one. So now there will be only one carbanion and it will obviously attack the other one. So in this case only, this type of cross aldol reactions are significant. Because if in cross aldol you are taking 2 carbonyl, both can generate carbanion, then there is mixture of compounds, there is no such synthetic value. But if you take this type of combination where one molecule there is no alpha hydrogen, now the cross aldol reaction has some significance. So what if different carbonyl compounds are reacted in aldol reaction? You have already seen different examples, but if you look at this A and B molecule, A molecule alpha hydrogen present, B molecule also alpha hydrogen present. So now all possible combinations you will get. So when A is generating the carbanion, that means it will act as nucleophile, it has some negative charge, right? So in that case, if A is generating carbanion, this is the combination. See, carbanion is generated from the red one, acetaldehyde. This is nucleophile. B will be acting as electrophile. Other possibility, if negative charge is generated in B, then B will be nucleophile and it will attack the red one. Electrophile is A. So these two are basically cross aldol. And the other 2 combinations, they are actually normal aldol product. So here 2 molecules of the blue molecule, that is propanaldehyde, is reacting with each other. So nucleophile is B, electrophile is also B, and the other possibility nucleophile and electrophile. So it is always better if you take one molecule with no alpha hydrogen, then you can get only 2 products. Sorry, one product. This type of, actually in that case also 2 possibilities are there. One is cross aldol, another one is normal aldol. So just have a look in the previous slide. Suppose Consider the first reaction, acetone and benzaldehyde. Here you have seen the products are cross-aldol product. But suppose if two acetone molecules are reacting with each other, then also there is formation of normal product. Though that product is not shown here because mostly this is the major product. Cross-aldol product is major here. And the reason is when carbonyl is generated in this position of acetone, it will obviously prefer to attack the carbonyl carbon of benzaldehyde rather than the carbonyl group of another acetone. Reason is aldehydes are more reactive. So that is why this is major. In all these cases, cross-aldol products are major. Normal products are not shown because they will be minor. So cross-aldol reaction, an aldol reaction between two different carbonyl compounds is called cross-aldol or mixed aldol. This is not very useful unless you take, especially you take care of the fact what type of molecules you are taking. So this reaction is not very useful if, suppose just take this example. It is usually a mixture of all possible condensation products, both normal as well as cross. So separation of them is really difficult. So you have to take one molecule where no alpha hydrogen. So here you can see three examples. One example you have already seen in the previous slide, formaldehyde, no alpha hydrogen. Then we have trichloroacetaldehyde. So acetaldehyde is CH3CHO, but if you remove all the hydrogens of methyl by Cl, now it is trichloroacetaldehyde. So this is alpha carbon, but there is no alpha hydrogen. So this is good for cross-aldol. Then the next reaction, trimethylacetaldehyde. You have replaced all the hydrogens by 3-methyl. You have alpha carbon, but you do not have alpha hydrogen. Fine. So some examples of cross where we have taken one carbonyl with no alpha hydrogen, but this one is there is alpha hydrogen. So carbonyl will generate here, it will attack formaldehyde. Now if you are thinking, is there will be no reaction between two acetaldehyde? Now there is also some logic, because when the carbonyl is generated, CH2CHO, acetaldehyde, this is the carbonyl. Now it will prefer the carbonyl group of formaldehyde. It will prefer this molecule to attack rather than another molecule of CH3CHO. Why? Both are aldehyde, then why it will attack here? Because here this is aldehyde, acetaldehyde, sorry, this is both are aldehyde, but here you have two H both sides, but here you have one H and one alkyl group both sides. So this alkyl group, it will have some plus I effect. So obviously if CH2CHO, this carbonyl is the nucleophile, the other part, that is this one, is better electrophile. I am writing E plus as electrophile. This is not very good electrophile. So that is why when one of the reaction partner is a CHO, then you will always get only one product. So here addition product is shown, not the condensation, because if you want to get it, you have to heat it. There is no heat sign, and then there will be double bond generation in this position. So the first example, acetaldehyde, formaldehyde. Second one, acetaldehyde and acetone. Some more aspects and problems we will see regarding this aldol reaction. Today we are at the end of the session. Thank you for listening.